let's get started with the afternoon session. And the first talk will be Michael Kastoryano talking about preparation of Gibbs states.
Thanks. It's a pleasure to be here. So today I'll talk about how to prepare Gibbs states efficiently on a quantum computer. As a matter of fact, the talk is very much about just applications of this new machinery of approximate recovery maps to problems in many-body physics. It's a good thing that the program committee didn't realize that, otherwise we would have ended up in the mega merger talk by Misha Woods. So I'll go over local recovery briefly in the first part of the talk, and then talk about the two applications of them, which is the efficient evaluation of local expectation values and the efficient state preparation or sampling of Gibbs states on a quantum computer based on some physically relevant assumptions. So the motivation for this should be quite clear. We've seen in a number of talks already that it would be very beneficial to have efficient Gibbs samplers to be able to simulate, for instance, strongly correlated or frustrated materials on a quantum computer once we actually have a quantum computer. But more and more there seem to be further applications of Gibbs samplers to problems, say, of SDP solvers, as Fernando showed, and to the problems of quantum machine learning. At least people claim this. But perhaps more importantly, the point of this talk is to really introduce these tools of recovery maps and convince you that these might be really important tools for the analysis of many-body systems. In particular, they can tell us something about exotic phases of matter. So I'll go very quickly over strong subadditivity, because we've already seen it a few times. We're going to see it more in the next talk. So we all know and love strong subadditivity of entropy. It can be written concisely in terms of the conditional mutual information, which is this expression here. We know that it's always positive. And it has all sorts of applications in quantum information theory. But to get an idea of an immediate application it might have in many-body systems is that it gives us sort of more information about the area law. So there's one of the basic conjectures of many-body systems is that the entanglement scales as the area of a region rather than as the volume. In terms of mixed states, the natural formulation of the area law conjecture is that the mutual information between a region A and its complement is upper bounded by a constant times the area around the region. And so what one gets, if we have a promise that the conditional mutual information is small, you create rings around your region, and you can show that in fact, considering the mutual information between A and just the first ring, or the first few rings, is almost the same as considering the mutual information between A and the entire system, as long as the conditional mutual information between rings is very small. And this comes from some telescopic sum argument. Furthermore, what we know is that if the conditional mutual information is strictly zero, then we get the existence of a recovery map, meaning conditional mutual information between A and C as a condition on B tells us that upon the erasure of A, you can recover the information on A just by applying a map on AB. So C remains untouched. And of course, it's symmetric, so the same holds for C. We know the exact form of this map. It's this Petz recovery map. And we also get that the state has a canonical form, meaning that it's unentangled. And there exists a disentangling unitary which only acts on B, which takes you not to this form, but to a form which is very similar. Now recently, some of these results have been extended to the approximate case. And in particular, what has been shown is that the conditional mutual information is lower bounded by a term involving the fidelity and the proximity of rho, and rho where you trace out region A and recover it with this rotated Petz map. And in fact, you can also get an upper bound. So these relationships are really very tight. Unsurprisingly, this theory is also related to the theory of proximate error correction, but I won't be talking about that right now. Now, beyond this, what I want to argue is that this conditional mutual information somehow gives us a partial classification of many body states of matter, or at least in the non-critical phases. Now, this is not a complete classification. You shouldn't take it all too seriously, but it is already known, it's called the Hammersley-Clifford, or quantum Hammersley-Clifford theorem, that if we have a full rank fixed density matrix, and we have a promise that for any regions A, B, and C, where A is simply connected, and B shields A from C, if we know that the conditional mutual information is always 0 in this configuration, it tells us that the full rank density matrix is in fact a commuting Gibbs state, meaning Gibbs state of a commuting Hamiltonian of local terms. And the converse is also true. Now, something which is not yet fully established, but we also get a partial extension of this result to pure states. And in this case, it takes the form of if a pure state satisfies this condition for any shielded regions, then it's going to be the ground state of a commuting local Hamiltonian. The other direction is already known. This direction, I think, hasn't been published, but it's not much of a stretch to show it. But importantly, in the approximate case, we're starting to realize that these results actually can be extended and generalized, because in terms of many body systems, these conditions are pretty stringent to have exactly a 0 here. What we're going to see in the next talk is that under certain circumstances, so in one dimension, you can show that for a full rank state where the conditional mutual information is not 0, but exponentially small as a function of the width of B, we get that the Gibbs state is a quasi-local Hamiltonian. And the converse is also true. This has only been shown in one dimension so far. It likely holds in higher dimensions. We don't know how to show it. And finally, we would like to generalize this equivalence as well. And right now, there are absolutely no results in this direction. But note that one of the directions is just a generalization of the area law conjecture. So it's plausible that this holds as well. What I'll be talking about today, though, is the dynamics. So all these results pertain to statics of systems. So you're given a state and you ask for properties of the state. What I'd like to talk about is rather the dynamics. So before getting into the quantum dynamics, I want to review what we know about classical systems, so classical Gibbs states. And almost the be-all and end-all of simulation in terms of classical Gibbs states are Monte-Carlo algorithms. And the idea is quite simple. You want to estimate the expectation value of a local observable, but weighted by Gibbs distribution. This Gibbs distribution is a probability vector that has exponentially many entries. So of course, you can't even write this probability vector down. So how are you going to estimate this expectation value, which is a sum over all entries of the probability vector? Now the trick is quite simple. In hindsight, you construct a Markov chain that has this Gibbs state as its unique fixed point, and you iterate the Markov chain. Now, the most famous example of this is the Metropolis algorithm, where you start with a random configuration of spins, for instance. You flip a given spin, you calculate the energy before and after your flip. If you've decreased the energy, you always keep the new configuration. If you've increased the energy, you only keep the new configuration with a probability which is proportional to the Gibbs factor. And then you iterate this as many times as it takes until your system reaches equilibrium. And then that gives you one sample, and you take the sum over a certain number of samples, which is going to be small. But the natural question is, when does your system actually reach equilibrium? And this is an extremely difficult mathematical problem that was addressed, for instance, was mentioned at least in the talk of Elizabeth Crossan. And surprisingly, for classical spin systems, there's a remarkably tight characterization of mixing times of the Metropolis algorithm. So in fact, it's a continuous version of the Metropolis algorithm called Glauber dynamics. And this theorem says that if the classical Gibbs states has exponentially decaying correlations, then the mixing time of the Glauber dynamics, so the continuous time Metropolis algorithm, mixes in time order log n, where n is the number of particles in your systems, the number of spins in your system. This in particular implies that L, so the generator of the semigroup, is gapped, but it tells you in fact a lot more, because gapped would only give you an order n mixing. This is remarkable because you know that for a critical phase, so say the two-dimensional Ising model below the critical temperature, your mixing time is going to be exponential in L. So somehow you skip an exponential and you go from exponential to logarithmic. So there's a double exponential separation between the two mixing regimes. And it's extremely tight. It's very general, it's independent of boundary conditions, it's largely independent of the specifics of the model. And of course, when we have this nice mathematical result, we'd like to find a way to generalize it to quantum systems. And this is what we did in a result presented 2 QIPs ago with Fernando Brandão, where we considered a natural generalization of Glauber dynamics, which coincidentally is constructed just from a Petz recovery map. So there you already see that there is this serendipitous occurrence of recovery in a problem which you might think is completely unrelated to start with. To make matters more interesting, this semigroup seems to be behaves almost the same as the natural dynamics that you would get from a weak system and environment coupling from quantum optics. And so we were able to prove a partial extension of this result. But this somehow was an unsatisfactory partial extension because it only held for commuting local Hamiltonians. So as soon as the Hamiltonians are non-commuting, we couldn't say anything. And our statics side of the equation somehow was slightly unnatural. So it would be extremely difficult, for instance, to verify it in an actual experiment. So now that we know that there's actually this connection with the Petz recovery map, we can say, okay, great. So you define a new Liouvillean, so a new generator of your semigroup, where you replace the Petz recovery map with this new rotated Petz recovery map. And likely the semigroup does converge and has the right properties, but all of the proof breaks down. So somehow the rest of the talk and the results that I want to present are an effort to control this non-commuting Gibbs sampler case. So we're going to take a completely different strategy. Okay, so to set the setting a bit more precisely, we consider a finite lattice, but that will eventually take to infinity. We consider a Hamiltonian on this lattice, which is Hermitian, a sum of strictly local Hermitian operators. And we define a Gibbs state on the lattice. In fact, we even define a Gibbs state on some restriction of the lattice, and this is going to be quite important in the proofs. The Gibbs state you're really interested in is the one that has a full lattice here, but we'll also need to use a restricted notion of a Gibbs state. So it'll be important to note that superscripts refer to the domain, to the support of the Hamiltonian, whereas subscripts refer to restrictions, so partial traces. So now I'm going to introduce 3 different types of approximations or conditions that we want to impose on our system. The first is what I'll call uniform Markov condition, and this is simply saying that the conditional mutual information between these concentric regions is small. Or more specifically, in fact, I choose a subset of the lattice. It could be this region ABC, or it could be this region ABC. And then I say, for any region A which is shielded from C in the previous lattice, then the conditional mutual information has to be small. In particular, it has to be decaying with L. And it's important to note that this condition, we'll need this condition to hold also for non-contractible regions. So these 3 regions are contractible to a point, whereas this region is not contractible to a point. It's only contractible to a ring, especially if you put this on a torus. Second condition is we want our system to satisfy decay of correlations, meaning the covariance between an observable in region B and an observable in region A should be decaying as a function of the distance between the 2 regions. And again, we need the stronger notion where it also has to hold on non-contractible regions. So again, now this is decay of covariance as a function of the Gibbs state only defined on the region ABC, so not defined on the whole lattice. And finally, we're going to need to use a tool developed by our chairman here, which gives us control on perturbations of Hamiltonians. So if we consider a local Hamiltonian on the lattice, H, plus a perturbation which is strictly local, then you can always write it as an observable V times the unperturbed Hamiltonian times the Hermitian conjugate of V. And these, operators OV are quasi-local, meaning you can truncate them at a distance L, and the norm is going to be exponentially decaying as a function of L. So this is an assumption. This always holds for local lattice systems. Fine, so 3 approximations. Uniform Markov, which is essentially the Markov condition, the Markov condition on conditional mutual information, uniform decay, which is natural of non-critical systems, and local perturbations, which always hold. And I denote the approximations by epsilon, delta, and gamma. So now the first result that we get is that if our lattice system satisfies uniform clustering, so the second of the conditions, then to estimate local observable on A, it's sufficient to consider the Hamiltonian only on B rather than on ABC. So the partial trace over BC of the Gibbs state on ABC is approximately the same as the Gibbs state on AB, where you trace out region B. So an immediate consequence of this is that local operators can be estimated efficiently, meaning you don't need to consider the Gibbs state on the entire system to get a good estimate of local expectation values. The proof is quite simple. You consider rho x, where x is region A, B, and C, and you compare it to rho AB, so this is really the Gibbs state only defined on AB, and the Gibbs state only defined on C, and you note that you can write it as a telescopic sum, where these rho xj plus 1 and rho xj are the Gibbs state with a Hamiltonian where you've removed terms one by one, and the terms you've removed are indexed by j. So you find out that this expression, which is the same as this one, can be upper bounded if you can upper bound each of the elements, but the benefit of upper bounding each of the elements is that they only differ at a single point on the Hamiltonian. So there's only a single Hamiltonian term where they can be different. But then we can naturally use this perturbation argument where you can express the unperturbed Hamiltonian, the perturbed Hamiltonian in terms of the unperturbed one with these operators j. And these operators j are again quasi-local, so you can truncate them and commute them through GA, which is only supported on A, so that you can express this local indistinguishability in terms of the covariance. And this was one of our assumptions, that the covariance has to be small. Now the main result uses these methods a bit further. So it says that if we have a full rank state, well, a Gibbs state on the full system that satisfies uniform clustering and uniform Markov with errors epsilon and delta on a d-dimensional lattice, then there exists a sequence of quantum channels, fd plus 1 all the way down to f1, such that f acting on any input state minus the Gibbs state is upper bounded by a term scaling as the volume and a sum of all of the error terms. Now the specificity of these maps is that each of these individual maps, fd1 to f1, are a tensor product of local maps. Not completely local maps, but maps that are order L local on the lattice. So it's pretty obvious to see that if the error terms decay faster than L to the D, we get a good upper bound on the convergence of the algorithm. Now, perhaps more relevantly, we can actually perform this iteratively. So we get say in 2 dimensions, you get 3 maps here. And then you take each individual map, which has order log L, which is order log L local, consider that your new lattice, and then reiterate the situation. And in this way, you construct strictly local maps, but now they're going to be log L, many of them. And it turns out you don't need these errors to be exponentially small to get this constant locality. They only have to be polynomially small. And now the proof is actually quite simple when it comes down to it. You cover the lattice with concentric squares, so 3 concentric squares. Now let's just focus on a single one. A minus is going to be the inner concentric square, the inner green one. A is going to be the red one, and A plus is going to be the blue one. And then we use the 2 properties that we assume, so Markov condition and decay of correlations, or rather local indistinguishability, to construct a map that only acts on this blue, red, and green region. So in particular, we consider, we first trace out the red and green region to obtain rho A complement. But we know that because of the Markov condition, there exists a quantum channel which is local only on the blue region, well, on the blue, red, and green region, which recovers tracing out the inside. So this gives us our first map. And then this state is the Gibbs state of the whole system where we've traced out regions A minus and A. But this is a hard state to work with. Instead, we'd like to consider the Gibbs state, which is restricted to, well, the Gibbs state which is not defined on A. So it's going to be this rho AC minus. But this state is going to be close, once you've traced out A, it's going to be close to simply tracing out the complement of A because of local indistinguishability. Now, when you put these 2 maps together, you obtain that in order to, well, acting with this local map FA on the lattice which is built by the Gibbs state only defined on the complement of A minus, you can reconstruct the full lattice. So, and FA by construction is going to be a local map. This NA in front comes from taking the union of all of these maps, because there are going to be NA different blocks. And of course, the support of these maps is going to be given by how good your approximation is. And the second step of the proof, once we've removed the A minus regions, we want to remove intermediate regions between the blocks that you took out. And you do this in exactly the same manner. So we first trace out the red and green regions and apply the modified Petz recovery map on these. And then by local indistinguishability, we say that we could have in fact started with the region that didn't have support on B. So that we get a second map, FB, by this construction. And now it tells us that if we're able to construct a Gibbs state on the complement of A minus and B minus, then we're able to reconstruct the entire system. So that already seems helpful. But then in the third step, you realize that the complement of A minus and B minus is a completely disconnected lattice. So these disconnected bits of the lattice can just be prepared by projection, again by a local map. So what we've constructed in the end are 3 local channels, one applied after another, that applied on any initial state will give us the desired Gibbs state up to an error which scales as NC, NA, and MB, where A and B and C are the number of regions we have to apply this trick to. So moral of the story, the entire lattice can be built from a local circuit of CPT maps. But now, we proved all of this for Gibbs states, but you might say a lot of the analysis didn't depend upon the fact that we had Gibbs states. So the proof ingredients required a form of local indistinguishability, which you can naturally define for ground states of local Hamiltonians, for instance. It required a form of uniform Markov condition, which you can also naturally define for pure states, in particular ground states of local Hamiltonians. But you also need a local definition of states. But this you obtain exactly when you consider ground states of local Hamiltonians. And it turns out by using a recent result of Martin Schwarz and Jens Eisert, you can apply the exact same proof to injective PEPs. So starting from decay of correlations and the Markov condition, you can derive an algorithm which prepares ground states of injective PEPs in a time log n, which is exactly the same scaling which was obtained by Yermin-Ge and Sirac with a completely different method. So this seems to be quite generic. And now what's interesting is there's a natural connection to the topological entanglement entropy. So if you remember in the proof, I said that we need the Markov condition and the exponential decay of correlations condition to hold on non-contractible regions. But one of the formulations of the topological entanglement entropy is specifically that the conditional mutual information between AC as a function of B on a non-contractible strip is going to have a fixed topological contribution. So it's not going to be exponentially decaying. So this tells you immediately that this theorem is not going to hold for topological systems, but this is exactly consistent with what we expect, because one of our definitions of topological order is that you cannot prepare it with a finite depth circuit. So this is very consistent, but even more so, we get that if the topological entanglement entropy is zero, and we have local indistinguishability, which, by the way, was one of the other definitions of topological order. If you have many ground states of a Hamiltonian, then it implies that there exists a local circuit. So it somehow connects in an interesting way two definitions of topological order with a third. And up until now, it hadn't really been known how to go in this direction. The other direction was known. Incidentally, Kitaev presented a similar result in an unpublished work in a talk a few years ago. So where do we go from here? Perhaps the most exciting thing about this proof is that it gives us a roadmap, in fact, for proving an extremely important open problem in many-body physics, which is based on some static properties of a state. Say, if you have injective PEPs and you know that they have exponentially decay of correlations, show that the parent Hamiltonian of this state is gapped. And it's our belief that methods similar to these will lead to a proof of the gap of parent Hamiltonians of PEPs. There's still some work to be done in terms of relaxing the assumptions on uniform decay. So this uniform decay assumption is a bit stronger than what you'd like. It's certainly a lot stronger than what you can measure in experiments. And generally, this is one of the very first applications of these ideas of recovery to many-body systems. We expect there to be many, many more. In particular, completing this classification seems to be an important problem. So, thanks.
Time for some questions.
Yeah, so you mentioned at the end that you think similar techniques might allow you to prove the gap of an injective PEPs. But in that case, I don't see why it should matter that it's actually injective and not like topological. Like your argument in the other case of why your methods don't work when it's not injective made sense. But to prove the gap, do you think you could also extend that to when it's not injective? Like
so I actually didn't hear. I didn't hear the question. You're asking why injectivity is important?
Yeah, for your sort of conjecture that you could use this to prove the gap of an injective PEPs. Why would that not work for, say, like G injective?
Well, the direct proof would cause a problem, obviously, because you would be preparing a state with a log depth circuit, and we know that topological models are typically not injective, and they also don't have a log depth circuit. So as a very first step, Yeah, to start with, we'd like to show this for injective PEPs. If we can show that, then of course it would be nice to generalize to G-injective PEPs, because we also expect topological models to be gapped. But it really seems to cause a lot more complications.
Okay, so you just think it's the method that might not work, but...
Yeah.
Any other questions? I'd like to ask one quick question. You mentioned that it probably couldn't be efficiently prepared if there's a non-zero topological entanglement entropy. We know examples where it can't be. But could you bound the amount of non-locality needed by the amount of topological entanglement entropy?
Well, I haven't thought about that. It seems to be pretty black and white. You really need these exponential tails. So I think it answers probably not, but I certainly haven't thought about it very much.
All right. Well, if there's no more questions, let's thank the speaker again.